Hi everybody, I'm Justin.
I'm Anna.
I'm Izuru.
And today we'll be covering SN1, SN2, E1, and E2 reactions and their mechanisms. So, we are now talking about SN2, which is bimolecular nucleophilic substitution reaction. And we have this example provided here. Generally, if a halogen is attached to a primary or secondary, in this case, it will favor substitution, and sodium sulfur hydride is a strong nucleophile, so it will undergo SN2. For the mechanism, it is a concerted step, which means the loss of leaving group and the nucleophilic attack will happen simultaneously. And so what will happen is the chlorine is going to take one pair of electrons with it, and it will leave in the solution. And then one pair of the electrons from the sulfur is going to come to the backside and attack the nucleophile. And then our product will look something like this. As you may have noticed, we have a change of configuration because this carbon center is chiral, and our product will have another chiral center. So an inversion of stereochemistry will happen. And so for SN2, there's going to be an inversion.
Hi, so I would talk about SN1 reactions, which is unimolecular nucleophilic substitution reactions. So we have this molecule right here, and this is the reaction with the weak base. So what will happen next is that the Cl will take the electrons and leave the molecule into the solutions. So it's just floating around, and it's just unreactive. Now it will give us the product with a carbocation intermediate. And this is when the weak base will come in and attack the carbocation. And then that will turn this into this molecule right here. And because the oxygen has 3 bonds, it is positive. Next thing, you will have another base molecule that comes in and basically deprotonate the group right here. Oh, nope. And these electrons will collapse onto the oxygens. That will leave us with the final products like this one. And because this molecule is achiral, you don't have to worry about the stereochemistry. But in case if the molecule is chiral, a racemic mixture will form. For SN1 reaction, it will favor tertiary alkyl halides to secondary and to primary. So this is tertiary alkyl halide, then to secondary and then to primary. The main reason is that tertiary alkyl halide will give us the most stable carbocation compared to the primary.
So we'll be doing E2, bimolecular elimination. It is a concerted mechanism, meaning simultaneously happen. The mechanism is like this. So they have a strong base. It attacks hydrogen. This bond goes to double bond, and then the leaving groups leave the compound, and then it ends up like this: double bond with the base, and then the leaving group alone. So it'll be the practice problem. This is the mechanism also. The compound, this is the leaving group, and OH is the base. So Na will be just like gone. So only consider HOs or OH. It'll be negative charge. And they're the original compound. And then these are all carbons. And there's 3 H's here. And then the electron will attack one of the H. And then the bond will go here. And then this will leave. So B. And then you get this plus H2O.
So we have E1, which stands for unimolecular elimination. And we have this example here with the bromide. So generally, if a halogen is attached to a tertiary carbon, and if undergoes a heat or a weak base, it's going to favor an E1 instead of an E2. And we will go over the mechanism right now. And so we have this problem. The first step of E1 is a loss of the leaving group. So this bromide is going to leave. It's going to take 2 electrons and break this bond. So we will be left with a carbocation intermediate step. And for the second step, there's going to be a proton transfer. And so we will use the ETOH. So these two, since there's going to be a proton transfer, we will borrow hydrogen in this carbon and essentially take that proton with us, and then this proton will break and it will form a double bond. And that is our final product.
Thank you for watching. I hope you enjoyed and learned something.
Thank you.
See ya!
Yeah.